Hello everyone, I am Sakib Shadab Sifat. Today I will be talking about the digital logic and circuit assignment and how I have solved it. So the variables are given here A, B, C and then it goes up to H. So the ICU bed maximum capacity which has been told me that it is B plus F plus H and according to the values it is 3 plus 5 plus 3 which is 11. So to draw the block diagram we need keypad, entry sensors and exit sensors, and all the three goes up to the 4-bit synchronous up down counter. Then it moves to the counter output. Here we can see it is a 4-bit comparator, and then it goes through the clock, and here we can see that it is an stable counter and it is a monostable counter. So in this page the steps has been outlined. So from the steps we can say that the system powers on and then it initializes system. Then if the counter is 0 it reads the maximum bed capacity from the keypad. Then if a patient enters and the entry sensor is 1, then the counter would be counter plus 1, otherwise then it goes to the exit sensor and then check. And if the patient exits or any patient exits, then the counter is counter minus 1 and then it will continue. On the other hand, comparator checks counter is greater than or equal max capacity. If it is yes, then the ICU is full, and which full means on. So the 555 monostable timer is on. The 7 segment display shows full. And on the step 9 it says if no bed is available then full will be equal to off. The 555 stable timer will be on. The 7 segment display being beds available. On the step 10 repeats the loop. System continuously monitors the sensor. And on the last step it says stop and then system turns off. So this is how the system works. On the flow diagram we can see that the flow says it starts and then it initializes counter, and from the read entry sensor to the display beds available, everything is under initialize counter. So let's go through it. First of all, it reads the read entry sensor, then it goes to the entry pulse. If the entry pulse is 1, then yes, increment counter, then the increment counter goes to the read exit sensor. The exit sensor reads it, and then if the pulse exits equal to 1, then yes, and it will say decrement counter. Then it will go through the counter equal to 1 or not. If yes, then it displays full, and if no, then it displays beds available. So what I have done is discussed here, and it says the following diagram shows the function of the components. Here ICU capacity is 11 beds, so we need to count from 0 to 11. We used 4-bit up down synchronous counter. This design ensures all flip-flop are triggered at the same time. This is how we have done this flow diagram. This is an image of 4-bit synchronous up-down counter. So we can see that here is flip-flop 1 and it goes through last to the flip-flop floor, and this is up-down counter. This is least significant bit, and this is Q0, Q1, Q2 and Q3, and here it is the 4-bit synchronous up-down counter. So let's go to the another topic, which is flip-flop, the input and the input down. So we have drawn here the truth table, and we have drawn for flip-flop 0, for 1, for 2 and for 3, which are given here, and the truth table which is up count and which is up or down equal to 1. So the truth table is given here according to the value which is 0 to 11. The 12 is not calculated here because after finishing the 11 it will automatically go to 0, so there is no need of doing that 12. And here is the values: q3 is the MSB, then q2, then q1 and q2, which is the least significant bit, and the decimal numbers. This is how the truth table has been calculated. Then if we move to the down counter, here it is. So it has been calculated the same as it was the previous one is calculated. So here is the clock which moves from 0 to 11. We do not need the 12. So the Q3, which is the most significant bit, and then the Q2, then the Q1, and then the Q0, which is least significant bit. And here comes the decimal numbers. So the Q3 is the most significant bit has been calculated here, which is 0, 0, 0, 0 and 1, 1, 1 that has been listed serially. Same goes with the Q2, Q1 and Q0, and same goes to the decimal number. The difference is in this here the decimal number is starts with 0 and it finishes with 11, and the same thing happens but it repeats from here 11, then it comes to 0. So on the second question it asked me to show the value of p, and according to the value of p and the values are A, B, D, E, and G. So the values that I have got from the numbers, which is 2, 3, 5, 1, 6, and multiplied by 2, which would be 34. Since the P 34 is less than 50, and so the condition meets, the D would be 100 minus P, which is 100 minus 34, and it would be 66%. And the frequency is A plus C plus 5, and according to the values A and C are 2 and 5, so 2 plus 5 which would be 12. This is how we need to calculate the T, which is 1 by F, and if we do it 1 by 12, the result would be 0.0833 second, and it would be 83.3. So to calculate the high TH, it would be D multiplied by T, and from the values we got the value of D is 66%, which is 0.66 multiplied by 83.3, which is 54.98. To calculate the value of T low, we need the value of T and the value of TH. So according to the value of T, it is 83.3 and the TH is 54.98. So if we do the subtraction, it comes to 28.32, and we have taken it as 29. And for the stable 555 timer formula, the RB is TL divided by 0.693 into C, and the RA is TH divided by 0.693 into C minus RB. So for the C, which is 50 microfarad, we need to calculate the RB and RA. So RB is calculated here. We know the value is 0. For the TL is 0.029 and 0.693 is constant, and the value C has been put here. So 50, which we need to multiply with 10 to the power minus 6, and the result for the RB is 836.94 ohm. For RA it goes through the same, and here it is the formula. We need to repeat the same formula here, and it has been applied here. Everything is the same. We need to change this value, and RB we have already calculated this. So the result is 1560 1586.72 minus 836.94, and the answer would be 749.78. For C, which is 250 microfarad, we need to repeat the same process, and it is RB and RA calculation. We have done the same process we did for the previous math, which is 50 microfarad, and we need to repeat the same process which is given here, 0.029 and 0.693, which is constant. We need only to change the value of 250 and multiply it with 10 to the power minus 6, and the result for RB is 167.38, and the RA value is 149.96. Then for another value C, which is 470 microfarad, we need to calculate the RB and RA again. So after calculating it, the values are 89.04 for RB and 79.76 for RA. So we have here right the discussion part, which is selected resistor values should be in the range of hundreds to thousands of ohms for practical 555 timer circuits. So C microfarad equal to 50 microfarad is the most suitable choice here. So the duty cycle verification here, DE, according to the formula we know, RA plus RB divided by RA plus 2 into RB, and the values we have got here, it is 749.78, then 836.94. So after calculating it, it comes 0.65, which is 65%. So we need to do the frequency verification, which is F, and the formula for frequency verification is 1 by 0.693 multiplied by RA plus 2 RB and multiplied by C. So we know the values for RA and RB, we need to multiply it, and after multiplying it, we got the value as 2423.66, which is the value for RA plus 2 RB, and the C is 50 into 10 to the power minus 6. As why we have taken the 50 into 10 to the power minus 6, we have discussed here, and here it is. We need the most suitable microfarad, which is 50 microfarad. So this is it, the frequency verification. It comes as 11.90 hertz, and it says that designing a circuit to active two segment display using two 555 timer. So this is an image or diagram for 555 timer of two segment, and here is R1 and then RL. Here is the resistors and R1, and it says the AB comparator, which is A less than B and A greater than B, and this is 7 segment display which will display the full. This is R and this is S and this is Q and Q bar, and here is also a resistor, another resistor, and here it is, we have another 7 segment display and it says another A greater than B comparator. So this is the overall overview of 555 timer 2 segment display. Moving on to the question number 3, we need to show all the values here. So the TH that we have already calculated is 54.96 meter per second, TL is 29 ms, P is 66%, F is 12 hertz. So the ICU beds that we have calculated before, it would be 11. For FSM, it says TH, if the TH is greater than 4, then it will be set. If TH equal to 4 or TL greater than 4, then it will set TL equal to 4. So here the conditions are, if TL equal to 4, then clock cycle, then TH equal to 4, then the clock cycle. So this is the state diagram. The state diagram goes from 0 to 1 to 3 to 4 and all the way up to the binary number, which is 1000. And after coming to 1000, it will not go to the another one, it will go directly reset, which is 0, and it will move here. So this is the state table. In this state table, I have calculated the reset state, then go by input state, and this is end state and the output state. The output state includes A and B. So the reset state, this is the values that has been given here, and this is the go by input values. The go by input by go values are 1 by cross, and then there is end state, it will go through the same as go by input. Then here it is the output state. The output state and B that has been calculated, it has been measured by the reset state, input by go state, and the end state. So talking about the equation part, here is the equation part. P0 next would be P3 bar, P2 bar, P1 bar and P0 bar plus P3 bar, P2 bar, P1 and P0 bar. Then plus P3 bar, P2, P1 bar and then P0 bar, and plus P3 bar, P2 plus P1 into P bar. Then it goes to reset. Then P1 next is P3 bar, P2 bar, P1 bar, and then P0. Then plus P3 bar, P2 bar, P1, then then P0. Then plus P3 bar, P2, P1 bar, P0, plus P3 bar, P2, P1, P0 bar, and then reset. And this is how the P2 and the P3 goes on and on, and in the final state the P3 is only the bar with P3, and the P2, P1, P0 does not contains any bar, and then it goes to the reset. And then output equation has been calculated here, same as the before, the A and the B, that has been calculated here from this truth table. So the HDL code is drawn here, which says the module ICU FSM system, then the input clock, then the reset go, and then output registration A and B according to the truth table. So the registration here 30 state, then we need to calculate if the state is less than or equal 4, then it will begin, and then case state which is 4b0000, so the state would be less than or equal, then it will go. And this is how the HDL code has been calculated and made. And here it is, the module ends here. And on the question number 4, it has asked me to draw some limitations and modification. So to solve this question, I have found some limitations that has been added here. So let's get started with the limitations. And the limitation, the first I arrived, which is limited counter capacity. The current system uses a 4-bit counter that can only count up to 15. Since the targeted ICU design requires 11 bits and 4 capacity is technically sufficient for this specific setup, but completely fails to scale beyond 15 bits without a structural design. That would be a problem in the future. So according to the values that we need to calculate, which is 11 bits, we need to calculate that is 11 bits, but here if we need 15 bits, it will be a very big problem. On the second part, the sensor reliability issue that has been shared here, false triggering or environmental noise at the entry or exit sensor can generate false pulses. This can lead incorrect up-down accumulation tracking than displaying a full state when bits are available, or vice versa. That would be a great problem too. Then the third problem that arrived, 555 timers instability. The output frequency and the duty cycle depends on the values of resistors and capacitors. Due to component tolerance, typically which is plus minus 5% to plus minus 20%, the actual output may slightly differ from the calculated values. So this may cause irregular blinking behavior, which is necessary to notice. Then moving on to the fourth on, which is no direct enable control. It says the 555 timer cannot be directly turned on or off controlled by the comparator. This requires adding extra logic gates or flip-flop to switch between displays. And moving on to the fifth on, which says display constraints, and it says a 7-segment display cannot easily show complex text like beds available or something like this. Doing so requires multiple displays and complex decoder circuits. So to talk about the modification part is only the higher bit counter replacement. So let's get started with it. So to talk about the higher bit counter replacement, it says that replace the baseline 4-bit counter with a 5-bit counter, as 5-bit structure expands the binary sequence counting boundaries from 0 up to 31, instantly doubling the infrastructure capacity. So it says basically that it will increase the infrastructure capacity if we increased it from 4 bit to 5 bit, or maybe even 6 or 7 bit. So lastly, the impact, which is increased structural complexity, that says migrating to a higher bit infrastructure systematically increases overall hardware logic gates, then flip-flop counts, system cost, and active power consumption. And the other one is connected circuits redesign. Since the counter bit changes, the digital comparator and display decoder circuits must be completely redesigned to support the new 5-bit size and maximize the count value. So it says that basically we need to change the counter bit, then we need to add the digital comparator and the display decoder that can change the redesign, or it can redesign the circuits.